It feels like just yesterday everyone was talking about hydrogen, hydrogen, hydrogen.
Right, the ultimate clean fuel.
But now, ammonia seems to be popping up more and more. It's kind of a surprising shift, wouldn't you say?
It is, yeah. A really rapid evolution, actually. It just shows how hard everyone's looking for, practical carbon-free options.
Exactly. So that's what we're digging into today. Ammonia and ACE. Could this actually be the fuel we've been searching for? We got this great article, Ammonia, the New Hydrogen, which really breaks down the pros and cons, the tech involved.
It's a good one. Covers the science, the potential, the hurdles.
Yeah. So our mission here is to give you the essential info, why the buzz, what works, what doesn't, and if it genuinely has legs as a future fuel. Think of it as your shortcut through the hype.
Cutting through the noise. So let's dive in.
Okay, basics first. Ammonia as a fuel. What are we actually talking about?
Okay, so chemically it's NH0, 1 nitrogen, 3 hydrogens. And the key thing, the really crucial part, no carbon atoms.
No carbon, which means
Which means when you burn it, you mostly get nitrogen gas, which is already most of our air and water. No C0. 0 carbon dioxide at the point it's used.
that's the big selling point, right? Zero CRO.
Yeah.
But does it actually, work as a fuel? Does it release energy?
Oh, absolutely. The bonds holding the nitrogen and hydrogen atoms together store energy. When you combust it, break those bonds, you release heat.
And that heat can power things.
Yeah.
Engines, generators.
Precisely. You can use it in an engine, generate electricity. It definitely functions as a fuel source.
Okay, so it burns clean, produces power. Now, one of the big headaches with hydrogen was always storing it, wasn't it? All that pressure, the super low temperatures.
Huge challenge. You need to get hydrogen down to like minus 253 degrees Celsius to liquefy it and keep it under high pressure.
Which sounds complicated and expensive. How does ammonia compare?
This is where ammonia really shines. It liquefies at much, much more reasonable temperatures and pressures. Think propane, like in a BBQ tank, around negative 33 Celsius, or just moderate pressure at room temperature.
Wow, okay, that's a massive difference. Propane versus space level cold.
Exactly. It makes storing it, transporting it, handling it just worlds easier and safer, too.
So less complex tanks, less risk, maybe.
Definitely. If hydrogen is like trying to bottle lightning, ammonia is, well, maybe like handling strong cleaning supplies. Needs care, but it's manageable. It's down to the molecules themselves. Ammonia molecules stick together better than hydrogen molecules do.
That makes sense. And I think I read something about energy density, too. Getting more bang for your buck in the same size tank.
You did. That's another win for ammonia. Volumetric energy density, how much energy you can pack into a given space. Liquid ammonia has about 50% more energy per liter than liquid hydrogen.
So for a ship or a truck, you could potentially go further in the same size fuel tank compared to hydrogen.
That's the idea, yeah. Very important where space and weight are critical factors.
Okay, so carbon-free burning, much easier storage, better energy density than hydrogen. Sound pretty good so far.
It does have significant advantages in those areas.
But
Yeah.
there's always a but, isn't there? What are the downsides? The challenges?
Oh, there are definitely challenges. Big ones. First off, ammonia itself is toxic and corrosive.
Toxic. How toxic?
Well, you wouldn't want to breathe it in significant amounts. It requires careful handling, proper ventilation, specialized materials for tanks and pipes because it can corrode things.
And doesn't it have a really strong smell?
Very strong. Pungent. The article mentions urine, which is accurate. And smelling salts, that's ammonia. It wakes you up fast.
Right. Not exactly pleasant if there's a leak. Okay, so toxicity, corrosiveness, smell. What about actually using it in an engine? Is it easy to burn?
Not as easy as gasoline or diesel. It
Yeah.
needs more energy to get it higher ignition energy. And it burns slower. The flame doesn't spread as quickly.
Which affects engine performance.
It can, yes. You need to design the engine specifically for it. But maybe more critically, there's the issue of emissions other than co-Euro.
Ah, like what?
Nitrous oxides, NOx. Burning ammonia, especially if not done perfectly, can produce NOx. And NOx gases are serious air pollutants. Bad for health, cause smog.
So you trade Q-Euro for NOx. That doesn't sound like a clean win.
It's a major concern. You need really advanced combustion systems, maybe catalysts, very precise control to minimize NOx formation. It's not a simple swap.
And standard engines just won't work. You need special ones.
Pretty much. Existing engines need significant modifications, or you need entirely new engine designs to handle ammonia's specific combustion properties effectively.
Okay, so it's definitely not a simple drop-in fuel.
Yeah.
But despite these hurdles, toxicity, knock-a-locks, tricky combustion. There's actual progress being made, right?
Yeah.
The article mentioned some examples.
Yes, absolutely. The momentum is real. Take Toyota back in 2023, they actually unveiled a working ammonia engine.
A car engine.
Yeah, a 2-liter, 4-cylinder engine designed to run on ammonia. That's a huge proof of concept for passenger vehicles.
Wow, so it's moving beyond the lab. What else? I think there was something about ships.
Right. An Australian company, Fontescu, they developed a ship engine that's dual fuel. It can run on diesel or ammonia.
Dual fuel, like a hybrid.
Kind of, yeah. Gives flexibility during a transition. And the impressive part, they actually sailed a ship using this engine, partly on ammonia, all the way from Singapore to the UK.
No kidding. A real ocean voyage.
A real voyage. That's a massive real-world demonstration for the maritime sector, which is desperate for cleaner fuel options.
That really does make it feel tangible. And wasn't there something about trucks and generators, too? Adapting existing stuff.
Correct. AA Power, a U.S. company. They're working on kits to convert existing diesel engines, the kind you find in big trucks, tractors, backup generators, to run on ammonia.
Conversion kits. So you wouldn't necessarily need a whole new vehicle or generator.
That's the potential advantage. Retrofitting existing equipment could speed up adoption quite a bit, rather than waiting for everything to be replaced.
Okay, so we're seeing new engines being built, ships actually using it, and ways to adapt what we already have. That's quite a bit of movement.
It really is.
Now, there was another angle mentioned, too, something beyond just burning ammonia directly, using it to carry hydrogen.
Yes. This is a really interesting strategy. A startup called Emoji, based in Brooklyn, actually, with backing from big names like Amazon and Saudi Aramco, is pursuing this.
So how does that work? You don't burn the ammonia?
Not directly in their main concept. The idea is to leverage ammonia's easier storage and transport compared to pure hydrogen.
Okay.
So you make hydrogen, turn it into ammonia, which is relatively stable and easy to handle, transport the ammonia, and
Then what?
then onboard the vehicle or wherever you need the power, you use a chemical process, a reactor or cracker, to break the ammonia back down into hydrogen and nitrogen.
And then you use the hydrogen.
Exactly. You feed that freshly released hydrogen into a fuel cell, which generates electricity cleanly, powering, say, an electric truck or bus.
I get it. So you use ammonia to solve hydrogen's transport problem, but you still get the end benefit of hydrogen fuel cells.
Precisely. It avoids having to build out a whole infrastructure for transporting and storing highly compressed or liquefied hydrogen, which is a massive barrier right now.
Actually pretty clever. Tackles a major bottleneck.
It's a very neat idea, addressing logistics head-on.
But, okay, this brings us back to a really fundamental point. Where does all this ammonia come from? Because if making it creates loads of CoO, then we're just shifting the problem, right?
You've hit the nail on the head. That's the elephant in the room. Right now, most ammonia is made using hydrogen that comes from natural gas methane.
And making hydrogen from natural gas releases CoO.
A lot of it, yes. Through a process called steam methane reforming. So today's ammonia, often called gray or brown ammonia, has a significant carbon footprint from its production. Using that ammonia as fuel doesn't help with climate change overall.
So we need green ammonia. How do we get that?
Well, the primary route is using hydrogen made via electrolysis.
Splitting water with electricity.
Exactly. If you power those electrolyzers with renewable electricity, solar, wind, hydro, then the hydrogen produced is effectively carbon-free. Green hydrogen.
And then you use that green hydrogen to make ammonia.
Right. Combine green hydrogen with nitrogen from the air using the Haber-Bosch process, powered renewably, and you get green ammonia. Truly zero carbon from production to use.
Okay, that makes sense. Are there other ways?
Yes. You could also apply carbon capture and storage, CCS, to existing natural gas-based ammonia plants. Capture the co-Euros produced during the process and store it underground. That makes blue ammonia low carbon, not zero, but much better than gray.
CCS, right. And the article mentioned something about finding hydrogen underground, naturally.
That's a newer, more speculative possibility. Geologists are finding evidence of natural hydrogen deposits deep in the earth. If we could actually tap into those reserves economically.
That would be a game changer, a natural source of clean hydrogen.
Potentially, yes,
Yep.
but it's still early days for exploration and extraction technology for that. So green ammonia via electrolysis is the main focus for now.
So the potential for clean ammonia is there, but it requires a huge shift in manufacturing, moving away from natural gas or capturing the carbon.
A massive industrial shift, absolutely.
Now, what about efficiency? You mentioned using ammonia to store and transport hydrogen, then breaking it back down. Doesn't that waste energy?
It absolutely does. That's a key trade-off. Every time you convert energy from one form to another, you lose some.
Like converting electricity to
You
hydrogen.
lose some energy there. Then converting hydrogen and nitrogen into ammonia,
Mm.
lose some more, transporting it, maybe minor losses, then breaking ammonia back down to hydrogen, another energy hit, then using hydrogen in a fuel cell to make electricity, more losses.
So it's like a chain of conversions, and each link leaks a bit of energy.
Exactly. Think of it like passing water through leaky pipes. Electricity, hydrogen, ammonia, hydrogen. That's less efficient overall than just going electricity, hydrogen, and electricity, or even better, just using the electricity directly in a battery electric vehicle if possible.
That's a really important point.
Yeah.
So while ammonia solves the hydrogen logistics problem, it introduces an efficiency penalty.
A significant one, potentially. And this leads to that fossil fuel reality check the article
Right.
mentioned.
What was that about?
Just acknowledging how incredibly energy dense and historically energy efficient fossil fuels have been to extract, refine, and use. The amount of energy you got back for the energy you put in to get oil out of the ground used to be extremely high.
And that's hard for alternatives to match.
It's a huge benchmark. We've built our entire modern world on this very efficient, albeit dirty, energy source. Transitioning means finding alternatives that are not just cleaner, but eventually, hopefully, nearly as effective and efficient in the whole system. That's the monumental challenge.
It really puts things in perspective. It's
Yeah.
not just about finding a non-polluting molecule. It's about the entire energy chain, from source to use, and making it work efficiently and economically.
Precisely. It's a systems level problem.
Okay, so let's try and pull this together. As we wrap up, what are the main takeaways on ammonia as a future fuel?
Well, on the plus side, it definitely offers major advantages over hydrogen for storage and handling. That's huge. And we're seeing real, tangible progress engines, ships, conversion kits. It's not just theory anymore. But yeah, the hurdles are significant. Toxicity and handling require care. The NOx emission potential needs careful management through advanced technology. And critically, producing it cleanly at scale is a massive challenge that needs solving.
Right. So lots of promise, especially for things like shipping, maybe, where batteries are tough and the hydrogen is difficult to store.
Mm-hmm.
But it's certainly not a perfect solution, not a silver bullet.
Definitely not. And that energy efficiency aspect, particularly for the ammonia to hydrogen route, is a serious consideration that needs work. You lose energy at each step.
Yeah. It's a valuable tool in the toolbox, perhaps, but maybe not the only tool.
Exactly. It could play a key role in decarbonizing certain hard-to-abate sectors. But efficiency and truly green production are paramount for its long-term viability.
Thinking about that efficiency point and the comparison to fossil fuels, it does make you wonder, doesn't it? Given how optimized our current energy systems are, even if they are polluting, what kind of really fundamental breakthroughs do we need? Is it just better chemistry, or do we need something more radical for truly sustainable, widely adopted alternatives to take over?
That's the big question, isn't it? Beyond just incremental improvements, what game-changing innovations in energy production, storage, or conversion might unlock that future? Definitely something to ponder.